Today we are walking through the paper titled SANAWM Efficient Minute Scale World Modeling with Hybrid Linear Diffusion Transformer.
What problem is this paper trying to solve?
The paper is about world models that can generate a full minute of 720p video from an initial image in the camera trajectory. The hard part is not just making pretty frames. The generated world has to keep the same scene identity, follow 6 degrees of freedom camera motion, and stay efficient enough to run on accessible hardware.
So the target is long-controlled video, not ordinary text-to-video generation.
Exactly. Earlier systems could produce impressive clips, but the paper argues that minute-scale action condition generation exposes 3 concrete weaknesses. The model state can drift over long sequences, camera control can become imprecise after video compression, and inference can become too expensive for 1 minute's 720p rollouts.
What does SANAWM change first?
The paper combines 4 pieces: a hybrid long-context transformer, dual-branch camera control, a second-stage visual refiner, and a pose-annotated training corpus of about 213,000 public clips. The goal is to keep the model stable over 1 minute while still following the intended camera path. Here is the architecture view. Text, video, and pose tokens move through alternating gated delta-net and softmax attention blocks. The gated delta-net blocks provide efficient frame-by-frame evolution, while the softmax blocks periodically anchor long-range spatial consistency.
Why mix those 2 attention styles instead of choosing only one?
Pure cumulative linear attention keeps memory constant, but it has no decay or saliency mechanism, so old features can keep the same effective weight as new ones. Pure softmax attention is expressive, but its cache grows with sequence length. SANAWM uses mostly frame-wise GDM blocks for compact recurrence, then inserts softmax blocks every 4th block to recover global anchoring. The paper uses this cumulative linear attention equation to show the baseline memory pattern. The state is a D by D matrix updated once per latent frame, so memory stays constant, but the sum keeps accumulating every previous value's contribution.
Where does the drift come from in that equation?
The state has no built-in way to forget stale features. At 1 minute length, that unbounded accumulation can make the recurrent state drift into stabilized training. The gated delta-net version adds a transition matrix and an additive update, so the frame state can decay, correct itself, and still consume all spatial tokens in one compact recurrence step. There is one more stabilization step. Because a latent frame contains many spatial tokens, the key energy can explode. SANAWM scales the keys by 1 over the square root of D times S, which keeps the transition non-expansive under the paper's trace bound.
How does the model keep the camera path precise after compression?
The camera control is dual rate. A latent trait UCPE branch captures the global 6 degree of freedom trajectory, while raw frame PL looker mixing restores fine camera motion inside each temporal VAE stride. That split is important because aggressive video compression can hide the small within stride motion that matters for trajectory following. The data pipeline is also part of the method. The author's Ray annotates even open source video sources with metric scale camera poses. Add rendered trajectories from static 3D scenes, then filter and caption the clips. That produces the 213,000 clip corpus used for action condition training.
Why spend so much effort on pose annotation?
Because the benchmark and training objective are about following continuous camera trajectories, not just matching a prompt. Metric scale poses let the model learn what a requested motion means in real 3-dimensional space, and the benchmark can then measure rotation error, translation error, and camera motion consistency. For evaluation, the authors build a 1-minute benchmark from 81st frame images across game style, indoor, outdoor city, and outdoor nature scenes. Each scene gets simple and hard revisit trajectories, so the test checks both camera following and whether the scene still looks like the same place when the camera returns.
What are the main numbers that show it worked?
On the main 1-minute benchmark, the refined SANAWM has the best action following among the compared world model baselines. Its rotation error is for 0.50 degrees on the simple split and 8.3s on the hard split, and its camera motion consistency is 1 point for 1 and 1 point for 4. For visual quality, its V-bench overall score is 80.62 and 81.89, close to Lingbot World while running as a 720p 1 GPU per clip pipeline. This qualitative comparison shows what those metrics are trying to capture. The green bordered SANAWM outputs preserve scene identity and viewpoint consistent structure under hard actions, while the paper reports that baselines often blur, change the layout, or collapse during the same kind of long rollout.
Does the second stage refiner only make frames sharper, or does it help the long rollout too?
It helps the long rollout, The paper reports that after refinement, revisit PSNR reaches 14.46 decibels on simple trajectories and 14.8 decibels on hard trajectories. More importantly, the long horizon visual drift score drops from 3.79 to 1.17 on the simple split and from 3.09 to 0.31 on the hard split. The efficiency result is the other key claim. SANAWM fits in 51.1 gigabytes without the refiner and reaches 24.1 videos per hour. With the refiner, the full pipeline remains inside an 80 gigabyte 100 budget at 74.7 gigabytes and reaches 22.0 videos per hour, which the paper says is 3.7 times faster than the fastest visible 480p baseline.
What evidence supports the specific G, D and scaling choice?
The training stability ablation isolates that point. Under identical 81 frame training conditions, the paper reports that the 1 over square root d times ASCII scaling is the only tested variant that converges stably. The Alta-style scaling hits an event at step 16. The deployment ablation then traces the speed path fewer than assigning steps, attention sync deployment, and then VFB for quantization. The distilled variant can denoise a 60-second 720p clip in third eye for seconds on a single RTX 5090. Which is why the paper frames SANAWM as an accessible open-source world model, rather than only a large cluster demo.
So what is the final takeaway?
The paper's central claim is that minute-scale controllable world modeling becomes practical when the architecture, camera conditioning, data labels, and refinement stage are designed together. SANAWM improves action, following over prior open-source baselines, keeps visual quality close to larger industrial systems, and makes 60-second 720p generation possible on much smaller hardware.
That makes the result feel less like one chicken, more like a full system design.
Exactly.